Welcome to another edition of the Far Out Journal Club. This is a service of the Alachua Astronomy Club, which is an amateur astronomy group located here in Gainesville, Florida, containing hundreds of members. The Astronomy Club meets monthly and features guest speakers on various technical subjects. This Far Out Journal Club is a separate feature of the club in which it's semi-regular, and in it, we stay away from strictly technical discussions, and we just explore more the fun side of astronomy, the cultural aspects of astronomy. So we've talked to guests ranging from science fiction writers and television personalities to observatory and planetarium directors, all trying to explore the side of astronomy that, of course, we all love, that first drew us to astronomy. Before some of us, such as our guest tonight, got a much more formal education in it. Rich Russin is the producer of this program, getting it all put together. And I am your host, Terry Smiljanich. I am a past president of the Alachua Astronomy Club. We would like to thank Dr. James Albury. He's the director of the Kika Silva Pla Planetarium here at Santa Fe College. And he hosts our monthly meetings and at his wonderful planetarium there at Santa Fe. Now, without further ado, our guest tonight is our pleasure to have as our guest Dr. Emily Levesque, astrophysicist and writer of the award-winning book, The Last Stargazers, an account of what it's really like to use some of the biggest telescopes in the world. From Hawaii to Chile, from the Very Large Array in New Mexico to the LIGO gravity wave detector in Washington State, from the Earth's surface all the way up to 41,000 feet in a telescope in a large airplane, a large telescope in a large airplane, the SOFIA project, which we'll hear some more about later. Dr. Levesque received her PhD in astrophysics from the University of Hawaii and is currently a professor of astronomy at the University of Washington in Washington State. Her research has focused, I believe it's fair to say, on red giant stars, their evolution, their sometimes violent endings, and of course she's ranged in other topics, but I think that's how she mainly was. Her initial focus was on. She's received a Guggenheim Fellowship. She's a Fulbright Scholar, and she's won many awards, including the 2023 Chambliss Astronomical Writing Award from the American Astronomical Association, and other awards that she's gotten for her technical research. She's the author of the book, as I mentioned, The Last Stargazers, which has won many awards, including, I think, named as one of Amazon's Book of the Year. So quite an honor. In it, she describes her personal journeys and experiences, learning how to use or take observations from some of the largest telescopes in the world, all the way from Gemini and Keck to some of these other huge scopes, including, in fact, visiting the Vera Rubin, which I think we'll hear more about later. The book itself is written for the general reader interested in exploring the cosmos. It's filled with spellbinding anecdotes, many of them hilarious, some of them frightening, but all of them edge of your seat stuff that I guarantee you, once you pick up the book, you won't be able to put it down. So we're so pleased to have her as our guest tonight. Dr. Levesque, Emily, if I may, welcome to the club.
Thank you so much for inviting me. It's great to be here.
Well, great. Well, let's get started with the first question that comes to mind. Why is your book called The Last Stargazers?
Yes, this is a very common question that people ask about the title, because it sounds a little bit sad, right? And the title is a couple of things. First of all, it's in part a reference to the way that technology is changing astronomy and the way that the role astronomers play in observations is moving. The book goes back and chronicles how we used to be at the telescope whenever we observed. In some cases, people were literally attached to the telescope. They were riding up in the prime focus at the top of the telescope all night. But things have changed really dramatically since then. When I was publishing the book, I was focused on how astronomers observe from, a nearby warm room in the telescope, or from a remote operating site, or I have telescopes that I can run from my laptop sitting on my couch. So where astronomers physically are has changed a lot. The pandemic happened between when I turned in the manuscript and when we finalized it and when the book came out. And it was really wild to watch the speed with which remote observing picked up from then, simply because it had to. So the Last Stargazers is partly a reference to, how where the observer is and how we stargaze has changed. I wanted to write a book that sort of saved the stories of how it used to be done. And it's also meant to be a little bit of a challenge to folks, because plenty of people still stargaze every day. There are astronomy clubs full of people who do this for the joy and pleasure of it. We have record-breaking numbers of students applying for things like astronomy PhD programs. So there's no shortage of stargazers. And what we are starting to face is that we need ongoing support for stargazers. We need the technology for us to keep doing what we're doing. We need to be able to employ people that want to work on astronomy. We want people that pursue astronomy for the pleasure to have the time and resources to do this with their leisure time. So we don't want to be the last stargazers. We don't want this to be both a changing art and a dying art.
Right. Well, let's talk about those old-fashioned telescopes, like the
Yes.
Mount Wilson, Mount Palomar, the 100-inch, the 200-inch, the ones that when I was growing up, these were by far the largest telescopes in the world. And you talked about the prime focus and about riding the telescope. We have in the planetarium where we meet, one of our members made a scale replica of Mount Wilson telescope. So some people can see the little cage that's up at the top. Tell us about what it was like working there and working with, instead of digital imaging, you had to use thin glass photographic plates. Is that correct?
Oh my gosh, these are some of my favorite stories to get from my colleagues, because by the time I was becoming a professional astronomer, this era was in the past. But oh my gosh, it was so great to hear people tell stories about this. And it started pre the actual night of observing, because you would indeed observe with photographic plates. I should have one right here, actually. I just moved into a new office, so I don't have everything at arm's reach yet. But photographic plates were these. They were these little thin sheets of glass that you would get delivered in bulk from somewhere like Kodak. And they're designed to darken when they're exposed to light. So astronomers would do all these sort of special tricks to these plates to try to get them as sensitive to light as possible, because they might be loading them into a camera and pointing the camera at something very dim. I talked to people who described, baking the plates, freezing them, flashing light on them quickly. They swore that helped. Or treating them with ammonia, with one guy swore by lemon juice, but anything that would make it as chemically sensitive as possible. The plate that I'm holding here is also the size of the very specific telescope that it was taken at. So they had to get sliced down to a size that would fit into cameras. And by the way, you did all of this work in the dark because the plates were sensitive to light. So somebody would prepare all their plates and then carry the plates to the telescope and get loaded up into something like the prime focus cage. I can actually show a picture of what it would look like for people to ride in the prime focus cage. There's a wonderful image that shows you just how big and just how high that cage is. So let me center it so you can see it nice and large. This is actually the Palomar 200-inch telescope, but you would be many, many feet above the ground, sitting in the prime focus cage all night. Astronomers would work with a night assistant who would help them turn the dome and operate things in the telescope while they were sort of trapped up there all night with the camera and with their photographic plates. It was freezing cold up there. Some astronomers took to wearing like old World War II era flight suits that they could plug in to stay warm. It was not always easy to get down to take care of biological needs, so extra water bottles were brought up on occasion. You can figure out the rest. And then astronomers would sometimes have to sit there for hours just pointing at a single object for a huge length of time so that the plate would slowly react to the light from the object enough to capture a clear picture. So it was a physically arduous time, but every astronomer I talked to who observed like this just like had a huge grin on their face while they talked about this whole process. They described playing music at night, walking between domes in an observatory, and you'd hear different music filtering out of every dome. Then at the end of the night, you would climb back down with your plates and go into a dark room and develop the plates to sort of fasten the image to the glass. And only then would your observing night be done. And only then would you have data that you could go painstakingly analyze by hand. Astronomy's gotten a lot faster and more efficient since then. Based on the mood of people when they told me these stories, I'm not convinced that it's gotten more fun because they all seemed to love doing this.
Yeah, I think one of the funniest stories you tell in your book, because to get up to that prime focus cage, like Mr. Hubble is there, you had to
Yes.
ride an elevator or a ladder or something up the side of the dome, and then climb over into the prime focus cage. And tell us quickly about the story of the astronomer chasing the operator.
Oh yeah. So first of all, I'm glad you mentioned this because this is a picture from right around the time that the 200-inch was turned on and having first light and being commissioned, which was in the very late 1940s. So that is Edwin Hubble posing with it for the photograph. But I'll back up and actually just show the interior of another telescope. This is a modern day telescope. This is the Subaru 8.2 meter telescope, but it gives you a sense of scale of just how high up you would be above the ground when you were at prime focus. So astronomers working up there would have a night assistant in charge of turning the dome while the astronomer themselves would control the telescope. And they would do something like climb up a ladder or climb up a little elevator that would take them up to the height of the prime focus before climbing in. There was an astronomer observing one evening with one of these very lovingly prepared plates. And he had been pointed at the same galaxy for the story that I remember being told was that he had pointed at it for more than one night, but at the very least for many, many hours. And this astronomer was famous for being a bit quiet, not the most communicative person there. So his night assistant decided to come out and check on him halfway through a very long exposure. And as the night assistant stepped through the dome, his jacket caught the light switch on the wall and he flicked on the lights in the dome. So the lights come blazing on, they go pouring into the telescope. They promptly ruin this beautifully crafted, carefully observed plate. And there's this just howl of fury from the top of the telescope. And the astronomer starts shouting and cursing and saying, what have you done? Like, you've ruined all this hard work. I'm going to get down from this telescope and kill you. So he starts turning the telescope and it kind of goes very slowly turning toward the elevator so that he could climb down and presumably go after this night assistant. The night assistant was watching him going, he seems really angry. I probably shouldn't let him down until I'm convinced he's not going to murder me. And the astronomer could spin the telescope, but the night assistant could spin the dome. So the astronomer's turning slowly toward the elevator, and then the elevator starts spinning away because the night assistant is spinning the dome. And it turned into this circular game of chase of the night assistant shouting, calm down, zzz, and the astronomer going, no, you've ruined everything. Zzz. And this happened at Lick Observatory in California, which has several telescopes on the mountain. And I always like imagining people at other telescopes looking over at this one, which was the biggest telescope on the mountain, in the middle of a beautiful night, and the lights are on, and the dome's just doing this, and going, what are they doing over there? But you can imagine the frustration of losing a perfect, beautiful observing night to someone accidentally flicking a light switch.
I'm sure the other astronomers are saying that must be some strange research he's involved in over there.
Yeah, it's like, what exactly are they observing? Yeah.
Okay, another quick anecdote I'd like to hear is one that in your book you say every astronomer, observational astronomer you talked to, when they heard you were writing a book about these sort of things, had the same question. Have you heard the one about the telescope that got shot? And when I heard that, I thought, whoa, what's that all about? So tell us about the telescope that got shot.
Oh yeah. So this came from a lot of my interviews, and I interviewed more than 100 of my colleagues for the book. And I really wanted to get a broad range of stories from people that had done all sorts of observing. I talked to these folks that had done prime focus observing. I talked to people that had been on airborne observatories that had operated balloons and rockets. And I really wanted people's own stories. But then I asked everyone, what's the one story I have to have in this book that you've heard like secondhand, third hand, 10th hand? Like, what's the tall tale of astronomy that has to be in a book like this? And so often everybody said, do you have the one about the telescope that got shot? So it took me a while to track this down. I wanted to talk to people who had been enough on site for the story that I told the real version. And it wound up happening at this telescope. This is the 107-inch telescope at McDonald Observatory in Texas. And this is indeed a telescope that got shot. And I feel it's only fair to point out that when I tell this story to a lot of people, I mention that the telescope is in Texas and everyone goes, of course. And the Texans who tell me this story were very precise and clarifying that the person holding the gun in this story was not from Texas, they were from Ohio. Just to be fair. But this telescope, shortly after it was built and had first light, infamously got damaged by gunfire. And when I asked people what the story was, this really had grown sort of tall tale status. And people imagined, you know, dramatic tales of like spurned lovers on the mountain, or a grad student who was mad at their advisor, or some like terrible shootout over the Hubble constant. And it was none of these things. It was an observatory employee who was unfortunately in the midst of a mental breakdown, and he became hell-bent as part of this on destroying the telescope. So he walked into the telescope's control room in the middle of observing one night and brandished a handgun at the operator and demanded that the operator lower the telescope to the floor, because he very specifically wanted to hurt the telescope, not the people there. The operator did so. Fortunately, none of the people involved in this were badly hurt. But he then pointed the gun down the barrel of the telescope at that beautiful new 107-inch mirror and emptied the clip into the mirror. Now, the telescope mirrors that we're talking about are made of the same glass that you see in, you know, a Pyrex dish that you use in your kitchen, but it's, you know, a foot and a half thick. So it's big, powerful glass. And you imagine shooting a bullet at glass and it shattering like the, you know, windshield of a car. And instead, the bullets just sort of went, and it was like throwing darts at a dartboard, and they just sort of wedged in the mirror. So after this happened, the gunman was, you know, a little underwhelmed at the result. He decided to go after the mirror with a hammer. Shortly after that, he was subdued and taken away. But the sheriff had been called and arrived on the mountain and looked down the telescope at the mirror to assess the damage. So this is what the mirror looked like after that had happened. You can see the sort of 6 bullet holes that had been left by the gun. The sheriff wasn't very familiar with telescope design, and so he saw these 6 bullet holes and the giant hole in the middle of the mirror. Folks who aren't familiar with design know that that's a hole for the Cassegrain focus, that light would bounce up from the primary up to a secondary mirror and down through that hole to go to a camera. The sheriff didn't know this, and he said, "Oh my God, the telescope's been destroyed." He must have thought he was shooting a bazooka. So word got out into the community that the telescope had been horrifically damaged. It made the news. I think Walter Cronkite showed the wrong picture, the picture of the wrong telescope shown upside down, but word had really spread that this had been a terribly destructive incident. And in reality, the observatory staff were looking at it going, this really isn't too bad. We can just kind of dig the bullets out. And we really just lost a little collecting area. So it's really just gone from the 107-inch to the 106-inch. So we're okay. But the director of the observatory still needed to share news of what had happened. So he put out an astronomer's bulletin where he carefully explained the harm suffered by the mirror from the bullets and preliminary blows with the hammer were extraordinarily small. So this is now one of the titles of one of the chapters in my book. The harm from the bullets was extraordinarily small. And to this day, the 107-inch mirror still has those bullet holes in it. They take it out periodically to be reluminized and recoded, and you can still see the bullet holes when they do it.
So it's still a useful telescope.
Oh yeah, in that same bulletin, Harlan Smith went on to say, you know, the very night after this happened, we got beautiful spectra of so-and-so, and like goes on to explain how wonderful the telescope is. And yeah, to this day, it's still working great. It's just, you know, got a little less collecting area.
Yeah. Now, you know, of course, we here in the astronomy club, many of us have telescopes, and you look, you know, you look through one end or you look through an eyepiece at the top, and we're used to that sort of personal interaction, you know, with what you're doing. I don't know that a lot of people have a correct image of what it's like to be in, let's say, you know, a 10-meter telescope observatory and actually using it for observation. I take it you're not standing at an eyepiece looking through it. Is that correct?
No, a lot of the biggest telescopes don't even have eyepieces anymore. This was a bit of a conversation of people saying, oh, I forget where I was, where we were talking about having, potential donors or supporters of the telescope come through and saying, oh, let's put an eyepiece on. And then someone going, do we even have one anymore? Like, I think they made one for Keck because it would just be so spectacular. But a lot of times now you will be anywhere from in a side room watching data show up on a screen to asleep when the observations get taken. There are telescopes like the Gemini telescopes. There's Gemini North and Gemini South. They're twin 8.1 meter telescopes, and they operate on what we call the Q system. I recently had a student get some time on one of these, and you plan out all your observations ahead of time very carefully. You say, I want to point at this star for exactly this long with this instrument, this filter combination, and then the data will sort of get emailed to you. So you just wake up and the data is ready for you to observe. And in between those two extremes are everything in the middle, operating a telescope from a remote operating station, from your laptop on your couch. So it's very different than being physically upon the telescope like it used to be.
Yeah. Now, you mentioned the fact that after you've planned all this and you have a particular place in the queue and a particular night and particular targets, things can interrupt it, such as wind or rain, clouds, things that we're used to here, amateur astronomers. Tell us about the probably the most unusual interruption in an observing schedule by someone who was at the what's the name of the
Was this the one
telescope in
here in
Washington?
Monastash Ridge here in Washington? Yes.
Tell us what
So
happened to that guy.
he had an interesting observing run. So first of all, I saw somebody in the comments reference the opening line of my book, which is, have you tried turning it off and on again? And that's a reference to something that happened to me at a telescope, and a great example of one of the many ways that observing can get disrupted. In my case, we were having a technical problem. We were wondering whether or not supports that held one of the mirrors in place were still working. And I've observed enough that I feel like I've seen almost everything that can go wrong at a telescope go wrong. We've had parts break. I've had a beautiful clear night, but the wind's been too strong to open. We've had hail, we've had rain. There's a lot of things that can interrupt an observing night. But the best story that I've heard in terms of, the planet or nature interrupting happened to a colleague of mine at Monastash Ridge Observatory, which is right here in Washington State. That adventure that I had where we were trying to reboot the telescope happened during some of the first observations that I was taking for my PhD thesis. And this story also happened to someone working on their PhD thesis. So I think there might be a curse involved here. But he was observing at this little telescope. We all call it MRO here at the University of Washington. And today it's mainly a teaching telescope. Back in the 1980s, it was a great place for people starting to do their PhD research. And to this day, that telescope still has its original night log up there, and you can go through and look at old log entries. Today, we all take notes on, our laptops or our phones, but on the night of this guy's observations, it was a man named Doug Geisler. He was taking very loving, careful notes, and you can look and see everything that's in the night log. He would say, it's May 18th, and I observed for 10 hours. I observed from 10 p.m. to 4 a.m., 6 beautiful hours of observing. I didn't lose any time to wind or rain or instruments breaking. It was perfect. The sky conditions were excellent. He had a fabulous night of observations for his thesis. And he went to bed, as you can see at the bottom of the log entry, about 5 a.m. So he woke up the next morning, and it should have been about noon, and he was opening the door of the dormitory where he was staying all by himself, and he was ready for, the blinding midday sun to sort of like start that groggy astronomer morning in the afternoon and get ready for another night of observing. He opened the door, and he opened it into just nothing. There was just blackness outside the door. He grabbed a flashlight and tried to point it outside the door, and the flashlight beam got swallowed after just a few feet, and everything smelled terrible. It was this awful, like sour brimstone smell. And he was remembering back to the middle of the night when he had sort of vaguely woken up around 9 or 10 a.m. because he thought he'd heard some really distant boom. He was now worried that he was living through nuclear fallout or the end of the world and had no idea what was happening, except that apparently the outside world had vanished. He went running back into the dormitory. He found a radio and started tuning it to figure out what had happened. And he finally heard a news report announcing what had happened. Usually when I told the story, everybody just goes, May 18th, 1980. But the story doesn't work here in Washington because everybody recognizes that date because that was the day that Mount St. Helens erupted. And to understand what happened with Mount St. Helens and Manastash Ridge, it's worth looking at a satellite view of this. The way St. Helens erupted, the side of the mountain basically blew off, and you got this enormous volcanic plume that went flying out to the northeast. So here's a little satellite map. You can see the oh, it didn't run. You can see the eruption starting to go off, and then you can see where Doug is. I want to see if I can get the animation to actually go. There we go. So there's the eruption. There's Doug at Manastash Ridge. He was sitting in the plume of the volcano. So his mountain was getting blanketed in ash. Like any good astronomer, he went running out to the telescope and he covered it because he knew that volcanic ash was corrosive and could do damage to the mirror. And then, like any good grad student, he went and took very careful notes. So he has this amazing log entry that's still there at Manastash Ridge. Hours lost, 6. Reason, volcano. Sky condition, black and smelly. Comments, I am the last survivor of the war. And he just dramatically writes out what had happened to him at the telescope. And the telescopes in Hawaii on the Big Island atop Mauna Kea are in pretty close proximity to volcanoes. They've had some interesting times where they've had to close for potentially corrosive volcanic fog. You would think that they would take the cake in terms of dramatically disrupted by volcano stories, but right here in Washington State is the most incredible one I've ever heard. And yep, that log entry is still there at Manastash Ridge.
I'm surprised Doug slept through the eruption.
He was far enough away. He was about 90 miles away. So I'm more surprised that he heard it, but you can, read research on just how loud volcanic eruptions get. And it's pretty wild that he was okay. He also was very careful about driving home because there's lots of advice out there on not driving your car during a volcanic eruption because that ash can get into and just gum up everything in the car. But he was able to carefully get home.
Okay, well, that's one problem we haven't had here in Florida with our observations. I don't think there's any volcanoes within 1,000 miles of us. Now, of all the places you've had a chance to visit where observations are made, and I mean, your book is filled with all over the world. One that is totally fascinating is going up in a large B747, NASA 747, with a large telescope on it. Now, it's called Sophia. Some of us have heard about it, but tell our audience about Sophia and what that was like.
Sophia is, I think, my favorite story in the entire book, and I have to show a picture of it. I know I keep pulling pictures up, but it's just too incredible to not show what this telescope looks like. So this is, or rather, this was Sophia. So Sophia stands for the Stratospheric Observatory for Infrared Astronomy, and it's exactly what it sounds like. It's an observatory that flies up into the stratosphere. So this is around 40,000 feet. It's a little higher than commercial airplanes fly. It's a specially modified Boeing 747 SP. It's the same model of 747 that they use for Air Force One. In fact, I guess they used to like swap parts back and forth sometimes. And you can see in the back of that plane that there is a sealed off telescope chamber with a door that's designed to open mid-flight, and it exposes this about 2.5 meter telescope that's optimized for observing infrared light. And the appeal of this setup is that infrared light is another great tool in the electromagnetic spectrum for studying the universe, but it's very hard to detect from the ground because it bounces off the water vapor in our atmosphere. But if you get up to 45,000 feet, you're above 95% of the planet's water vapor. So you're able to detect a lot of infrared light that you can't get from the ground. And it is easier to do this, as complicated as Sophia is, it's easier to do this than to launch something fully into space. So for years, Sophia operated as an airborne observatory. It would take off, fly around, and you would point the telescope out that open back door of the plane to observe whatever it was you were interested in. So I got the chance to observe on Sophia. I actually flew on it during one of its Southern Hemisphere deployments. It flies out of Christchurch, New Zealand. It operates with the National Science Foundation's Antarctic Research Center. We actually flew so close to Antarctica that we got to see the Southern Lights from the cockpit of the plane, which was the coolest thing I've ever seen in my job. And I got some beautiful data from it. But it's a wonderful observatory. Until JWST launched, it was the best tool that we had for a whole window of the electromagnetic spectrum, studying infrared light. And unfortunately, it got defunded and shut down in like fairly recently. But it's really a shame that it's not flying anymore, because it was such a unique and such a useful instrument. And it was the last so far in a series of airborne observatories that sort of took advantage of this middle ground between observing on the ground and observing in orbit or beyond.
I'm surprised, being in an airplane like that, how could they keep the image still enough to get data?
So, fun fact for parties, Sophia operated on the world's largest ball bearing. I'm trying to remember exactly how big it was in diameter, but it was this ball bearing that would float 1.2 meters in diameter. That was it. It was sealed into the mount of the telescope along with just basically grease. And it would float on this sort of oil that would let it stay and sort of act like a gimbal and stay supported. One of the nights that I was supposed to fly on Sophia, we actually had to scrub our flight, because even in Palmdale, California, which is where it flies from in the north, it was too cold and the grease was starting to sort of gum up, and the telescope would not have floated. It would have sort of jittered around with the turbulence of an airplane. It was really cool to watch during the flight, because from the part of the telescope where people fly, you could see the back end of the telescope itself. And we would be bumping around and moving a little bit with the plane, and it would just be floating perfectly still. It was really cool to see.
Oh, wow. Well, I think it's probably fair to say now that Sophia it's no longer, it's been shut down, right?
Mhm.
And
Yeah.
I think probably isn't the James Webb telescope going to explore the infrared in much more detail?
So Webb is going to be amazing for the infrared, and Webb operates out to what we call the mid infrared. Sophia actually observed at longer wavelengths than Webb is able to reach. And this is partly just the factor of no two telescopes are identical, and each telescope is better at different things. And I mean, Webb is a beyond astonishing
Yeah.
observatory. It is absolutely incredible what it can do. But there's a couple of things that Sophia was able to do that we now don't have the capability for. So it's too bad that we weren't able to support both.
Okay. Now, as a working professional astronomer, walk us through the process, if you would. Let's say you have a project, a research project in mind. I don't know, let's say looking at planetary nebula envelopes to determine the composition of the original star.
Mhm.
You have a specific research in mind. What are the steps you have to go through to get time on, let's say, a really big telescope like Keck?
So the first step for getting time on a telescope like Keck, I'll use the exact example you've given me, is you have to be at an institution that has access to Keck. Some telescopes, and in fact, even Keck, have some amount of time that anybody can propose for, but time is the precious commodity at a telescope. So you apply for time the way other subfields apply for grant money. NASA has a small share of Keck time, somewhere like the University of Hawaii, where I went to grad school, has a share of Keck time. So you would prepare to write a proposal asking for time on Keck. And the proposal would be the result of a lot of very careful math. So you would say, all right, I want to study the chemical composition of planetary nebula, which means you're probably taking either a spectrum or you're taking pictures in very, very narrow wavelengths that can show you, hey, I'm seeing glowing hydrogen or glowing nitrogen or oxygen from that nebula. So you would put together a careful proposal saying, I would need 3 nights on this telescope, or I would need 12 hours on this telescope, because I want to point at these 3 planetary nebulae. And I need to point to them for at least 2 hours apiece to get as much data as I need. And there's resources online and a lot of math that you learned in grad school that helps you calculate exactly how much time you needed. And then you write your sales pitch and you say, here's why planetary nebulae are important. Many more people want to use Keck than we have time available. So you have to make an argument for why we would point to a planetary nebula instead of a potential exoplanet or a distant galaxy that could help us figure out the Hubble constant. And once you've written that argument up, you submit it to a committee. The committee reads all of these proposals, carefully discusses them, ranks them, and the highest ranked proposals are granted time. And in a case like Keck, they would come back and say, you have March 6th as the night that we've given you, and then you have April 6th and May 6th or something like that. And when I show up at the telescope on March 6th, I have to hope that there are no volcanoes, that it is cloudy, that nothing's broken, because if it is not a good time to observe on March 6th, if anything goes wrong, I can't just stick around and observe on March 7th because somebody else has been allocated that night. And it leads to a funny sense of urgency at a telescope, because you'll also be reminded at a telescope like Keck, you know, every hour of this telescope running costs $10,000. And they're factoring in how much it costs to build the telescope and how much it costs to maintain it. There are engineers on staff. There are janitorial staff. There are cafeteria staff on the mountain that support the people who work at the telescope. There are operators who professionally use it. There are astronomers who are experts on every tiny detail of how Keck works. And all of that has to be funded in order for Keck to be working. So every astronomer shows up keenly aware that you can't waste a single second. And you usually have this beautiful plan saying, oh, I'll point at this star for this long, and then I'll point at the first planetary nebula, and then I'll point at the second one. And usually the plan works great for like the first 15 minutes, and then inevitably something goes wrong, and you have to sort of scramble to rearrange it. So it's a busy and sometimes nerve-wracking night. But at the end of that, you have a bunch of beautiful data in raw digital form. And then you go back to your office and you or your research partners analyze the data. And that can take plenty of time on its own. And only then do you have a very clear picture of what you have and what comes next. Very talented astronomers can analyze it in real time at the telescope as they go, but that takes practice, and that usually takes teamwork, because if you're there by yourself, you're usually just scrambling to get the next observation.
Well, yeah, again, I just thought we'd like to hear about those nuts and bolts of what's actually involved in all that. Now, tell us about, some people want to hear about the Vera Rubin Observatory down in Chile. And it
Yes.
relates to another subject, another chapter of your book about targets of opportunity, which are, you know, very quick astronomical events that no one's expecting. No one's happened to be looking at that exact spot at that moment. A supernova, for example, a large supernova. Vera Rubin is going to change the playing ground on these targets of opportunity, aren't they? Isn't it?
Yes. So I can talk about the targets of opportunity first, because that's the title of one of the chapters in my book. And I was writing my book while Rubin was being built. I was actually writing my book in keeping in mind that I wanted to finish it before Rubin came online. And unfortunately, the pandemic delayed things a bit. But Rubin is having its first light practically as we speak. They have put their beautiful new camera on the telescope, and it's starting to operate now. So I'll get to that in a minute. But prior to Rubin, we had other telescopes like it. And it's the latest example of what we call a survey telescope, where telescopes will observe the same patch of sky or the same objects repeatedly, or try to get a very complete picture of the night sky. And something like Rubin is specifically looking at how things change as a function of time. So you'll point to a galaxy, point at it again, and see if the tiny dot of a new supernova has appeared. When something like a supernova happens, or something like a gamma ray burst, or when you say spot a new asteroid, there's usually a scramble to study it as quickly as possible. You want to point other bigger, more powerful telescopes at it to get a spectrum of it and measure its chemistry, or keep an eye on it to see if it's getting brighter, getting dimmer, staying the same, varying. And something like that can ruin the plan that I just described of sitting carefully at Keck pointing at planetary nebulae. I've been observing at Keck and gotten a phone call saying, you should stop everything you're doing and point at this object. Sometimes that's just colleagues who know you're there and count on your goodwill. Sometimes telescopes have official programs where they can kick you off the telescope and say, this very rare event has happened, and we promised these people that if such an event happened, we would kick everything off the telescope and point it to this. Hubble and Webb have this capability too, if something sufficiently exciting happens. And it's great because sometimes these events are shockingly short-lived. But on the flip side, it's hard to plan for, and it makes for a very chaotic evening when you're trying to chase something that might not be around very long. So in principle, this happens whenever some weird new thing has been discovered. And what Rubin is going to do is Rubin is an 8.4 meter telescope that's almost done being built down in Chile. It has, I think, I'm trying to remember the exact number, gigapixel camera that is going to basically take an image of the entire southern sky every few nights over and over again for 10 years. So it's going to give us a decade-long movie of the night sky. And the size of the telescope and the sharpness of the camera combined are going to revolutionize, doesn't feel like a strong enough word for what it's going to do to how we study targets of opportunity. A good comparison number is the scale of supernovae that it's going to discover. So these are exploding stars and these things that you see as just these sort of little pinpoints of light. And right now we discover maybe like 1,000 supernovae, a few thousand supernovae every year. Rubin, by comparison, is going to be discovering 1,000 supernovae per night. So right now, when we discover a weird supernova, we get maybe a couple of months and we can grab a telescope and follow them up. An entire challenge with Rubin is just a sheer big data computational question. When you get 1,000 supernovae every night and you get 10 1 in 100 events, how do you decide which one to point a telescope at? What happens if the next night an even crazier one happens? So this is a very ongoing problem in astronomy. I'm proud to say that the University of Washington is a big leader in this too. We're one of the founding partners of Rubin, and I have colleagues that are experts on machine learning, on artificial intelligence, on ways to sort of computationally attack this problem so that we can prioritize the heaps of data that Rubin is going to be producing and how we can point telescopes at it. The big pinch we feel right now is that there are not a whole lot of world-class telescopes out there, and we will very, very easily and very quickly run out of the number of things that we can point at exciting stuff that's coming out of Rubin.
So we're not exactly the last stargazers. There's a lot more stargazing in our future. We're really looking forward to what the Vera Rubin will come up with. One last question, and we're not on any time limit here, but one last question I wanted to ask that's not in your book is, tell us about arachnoastronomy.
Oh no. Okay, so I'll explain arachnoastronomy. So this was not in my book because it didn't technically happen at a telescope, although you can find a lot of stories about weird spiders at telescopes. Some of our best observatories in the world, I just mentioned Rubin, are in Chile. Chile has big tarantulas and they love hanging out at telescopes. There's some people that swear they're good luck. They're a little frightening when you see them, but they're actually very shy and harmless. The arachnoastronomy that you're talking about, though, happened here at the University of Washington. And I think it's my favorite example of Twitter and science Twitter being used for good. And what had happened was we had a hatching in our department of jumping spiders. We think there was like a nest somewhere in a ceiling panel. And these little jumping spiders that are, again, utterly harmless, started practically raining down from the ceiling onto the desk of one of my postdoctoral researchers. Her name was Jamie Lomax. And she was getting irritated by the spiders, but not terribly scared of them. She put a call out on the internet saying, "It's raining spiders on my desk, what do I do?" And someone said, spiders like that, spiders that jump and attack their prey instead of building webs and wait for their prey, will chase laser pointers. And we all saw this and went, no way, we got to try this. I had some spiders in my office too, and I reached into my desk to test what I just read. And I had 2 laser pointers. I had a green one, which is helpful for pointing at things in the night sky, and I had a red one that I used to teach. So to me, this made total sense. This is what any scientist would do. I had a spider on my wall. I had it chase the green laser pointer and it was really excited. And I had it chase the red laser pointer and it was kind of not that into it. And I put the 2 videos on the internet saying, what does this mean? Can spiders see color? I don't know. And this was when Twitter did its thing. Spider Twitter found us and started passing this tweet around saying, does anybody research color vision in spiders? And someone went, oh my God, I do. I can explain this. Here's how it works. Wait a minute, we can figure out exactly how well spiders can see. Like somebody did the math and figured out that spiders like this can see the moon, like they know the moon is there. Our department wound up inviting the spider scientist at the heart of all this to give a presentation in our department, because it turns out spider eyes are actually shaped kind of like little telescopes. They have a forward and a backward lens that help focus the light, and they have receptors for different colors at different focal points, which helps them avoid chromatic aberration. So it was a really interesting talk because it got us pitching around ideas for, could this be part of a creative new telescope design? I've seen proposed telescope designs that are based on things like a design for lobster eyes and their ability to see 360 degrees. So it was goofy, but some fun science came out of it. And now when we find a spider in my house, I can just lead it outside with a laser pointer. So yeah.
Well, that just shows what a broad career you've had and experience, all the way from 41,000 feet down to jumping spiders in your office. I think we'll probably turn this over now. There's a lot more I would love to have talked about: radio telescopes, the Arecibo and Green Bank collapse of those large radio telescopes and all. But I do want to turn this over to the audience, because I already see some very interesting questions that have come up. The first one by Dave Froiseth. Dave, or I don't know, should we unmute Dave, or should I just ask his question?
I'm fine with either. Yeah.
Okay, well, I'll ask the question for him. Dave wants to know, has Starlink impacted observations you or people you know of in any way?
Yeah, tremendously, especially for observatories like Rubin. Again, right here at the University of Washington, we have people researching satellite constellations. It's not just Starlink, and trying to mitigate the effects of these. The difficulty with something like Starlink is you're launching a bunch of tiny satellites into Earth orbit low enough that they can sort of be used to help distribute an internet. And because they're that low, they're very good at reflecting sunlight. As they get all the way up to altitude, this reflection decreases somewhat, but the basic consequence is you have a lot of really bright satellites in orbit. And when a satellite passes through any image, folks that have done any kind of astrophotography are familiar with this. You get this little white streak that just cuts through your image. When this happens to observations at something like Rubin or other survey telescopes, and when this happens with Starlink, where there's a bunch of satellites together, it looks like a cat clawed the image. And it looks not pretty when you look at a picture, but at a glance, it doesn't seem tragic. And I've heard plenty of people ask, well, can't AI fix this? Can't you just fill in the gaps or just take another picture? And you absolutely can if you want to make the image look nice. What you can't get back is if one of those supernovae was behind one of the satellites, or if something that you're trying to monitor carefully is behind one of the satellites. And there are so many of them in orbit these days that it is non-trivial how much of the sky they're going to block. So this is where we're currently running into trouble, is you permanently lose time-dependent information on these objects. So I know that astronomers have had discussions with the American Astronomical Society, with the FCC, and that's currently the governing body that decides what can be launched. They've had conversations directly with SpaceX and some of the other satellite constellation programs, trying to talk about ways to mitigate this. And it's everything from, can you paint them black, which helps, to can we really limit how many of these get launched, because Earth orbit is going to become a appallingly crowded place very soon. By the way, everything I'm talking about is optical imaging, or the type of imaging that we're imagining with light that we see with our eyes. Radio astronomers are having an even more difficult time of it, because the satellites communicate at radio frequencies that can interfere with observations. So it's a complicated issue, and right now the different interest areas are very much at odds with one another. So I'm glad we have people in the field focusing on how to solve it. I'm glad that we've been able to have something of a conversation along these lines. I have no idea how that's going to evolve going forward.
Okay, well, Laura Foley in our audience, she noticed behind you on your bookshelf the Carl Sagan book Contact, and she wonders, was that an influence on you? And also, what other influences did you have growing up that got you so interested in astronomy?
So most definitely Contact. And what's funny is you can see the nice book that I got from a bookstore recently. What you can't see is the copy that I had when I was a kid, which is falling apart, but which I can't bear to get rid of. But yeah, so Contact, the movie, and Contact, the book, were both huge inspirations for me. I loved the story period about a little glimpse of what it was like to be a professional astronomer. Even as a kid, I knew you probably didn't discover aliens like every night, but I didn't know any astronomers growing up. I didn't know any professional scientists growing up. The area where I grew up did not have people working at universities, working at observatories, and nobody in my family had a PhD. Nobody in my family was a scientist. So movies like Contact, or like, I really liked Twister, Jurassic Park. Not representative of the typical scientist experience, but I at least got to see scientists depicted as heroes and women depicted as scientific heroes, which was cool. I also loved Contact because Carl Sagan is an exquisite writer, and I've always liked science. I've also always liked writing. All of this came back specifically to me writing The Last Stargazers because I wanted to give people this glimpse that I would have loved as a kid, and that I know a lot of people live and enjoy now, of what it's actually like to be a scientist. I think those were a lot of my biggest inspirations for going into the field. And then just like reading about people that got the chance to be part of these huge endeavors, like creating and launching the Hubble Space Telescope, even reading about things like the Apollo program. I loved the idea of all these people getting together and being supported and trying to do just these amazing, bold scientific things. It was really heartening growing up to read about stories like this.
Okay. I, I I don't know, Rich, if maybe Rich can be unmuted. I don't know if there are other questions from the audience that you've noticed that we ought to be asking, and or whether somebody has their hand up and can be unmuted for that purpose. Rich, what do you think? How should we do this?
Well, I did see a question in here earlier about more about the James Webb Space Telescope. One person asked, is the JWST considered to be terrestrial?
No, JWST is very definitely a space telescope. It's about 1 million miles from Earth.
Okay. And that's what I think it followed up there. Uh, Looking through, I don't see any more specifically. I'm seeing lots of people thanking you for your time and your energy and enthusiasm here. Um,
I have let me ask this question. One of the things that we're starting to see in our club, people have some of our club members have very large telescopes, 17-inch, larger, and some of them have very complex, intricate imaging systems that they can use. But now, of course, we're seeing these small little robotic telescopes, I guess you'd call them, about this big, and you set it down and it figures out where it's at and it starts taking images and starts stacking them as you go along, and then sends them to your iPhone or your iPad or something, and you can actually watch a developing picture of the Orion Nebula, let's say, that looks better than pictures I used to see as a kid taken from Mount Palomar. I mean, these are just beautiful, beautiful images. And to me, that's sort of almost a parallel to something that's going on in astronomy, which is, you no longer have to climb up to a prime focus in the freezing cold, dealing with fragile glass plates. You can be sitting in your office with a laptop, receiving data and crunching it, analyzing it. And I guess that's sort of one of the overall themes of your book is the fact that some parts of astronomy are getting separated from the actual thrill of looking with and using your eye as the optical receptor and seeing something firsthand.
Mhm.
How do you see this going in terms of astronomy?
It's an interesting question because there's no substitute for getting it through your eyes. And I think that technology can be really democratizing. I think it makes it easier for people to take their own pictures. I remember when we had the huge coronal mass ejection back in May, and a large swath of the US was able to see the aurora. And everybody got way better aurora photos on their phones than they did with their eyes because our phones sort of automatically stack images. I think that an interesting thing when I wrote my book was that I didn't ask anybody, how did you get into astronomy? I wasn't looking for astronomer origin stories. I just wanted their wacky observing adventures. And everyone told me their origin story anyway. And some of them were, I looked through a telescope and I saw Saturn's rings, or I saw the Orion Nebula. But some of them were like, I grew up in the middle of a city and I never saw stars, period, until I went to a planetarium show. And then it blew my mind to know what was up there. Or I finally got the chance to play with astronomical data on a computer and I couldn't believe what I was seeing. I was part of SETI at home or something like that. So I think we can use the tech side of things to help people get excited, but recognize that it shouldn't be a substitute for actually getting to use your eyes. I'm sure you all are more familiar with this than I am, but I have people ask me sometimes, hey, I want to get into astronomy. What type of very expensive telescope do I have to buy? And I always tell them, you can just use your eyes. You can get a pair of binoculars and point them at the moon. And I think keeping in mind that just anything that gets you looking up is good, is a way to keep taking advantage of that.
Yep. Yeah, we get lots of new members, and that's one of the first questions they ask. And we have a lot of people that have a lot of advice to give them. But as you say, even a pair of binoculars can open up the universe for you. We have one question. We're running out of time, perhaps, but we have a question from one of our past presidents, Jerry Cheney. He said he really enjoyed your great courses videos and wondered if you have any more planned.
No, thanks for asking. Yeah, I did a lecture series with the great courses called Great Heroes and Discoveries of Astronomy. And it's not unlike the Last Stargazers, but it's sort of a different batch of stories. It's looking at the big discoveries that we've made in the past 100-ish years, and then also the people behind them and all the different ways that you can be an astronomical hero. So this is everything from, Edwin Hubble and his night assistant, Milt Humason, taking the observations that gave us Hubble's law, to the thousands of people that built gravitational wave observatories. It was a very fun lecture to do. They actually did ask me to do a second lecture, and then they unfortunately had to put a bunch of their lectures on hold. I'm hoping to do something with them on, I call it the weirdest things in the universe. So weird stars, weird galaxies, weird planets, weird enormous things. I had the course outlined and was starting to write it when we unfortunately had to cancel it. And it's actually been on my mind that I'd love to prod them about this again. I'm similarly thinking about the next book that I would be interested in writing. So hopefully I'll have more official news along all those lines soon.
Great. And you've seen a transition going on in astronomy with regard to gender. It used to be, there were very few women, female astronomers. Now there are, of course, more and more. And now we have the Vera Rubin Observatory finally recognizing one of the great heroes of astronomy. Right now, do you see that as a growing trend?
It's been really wonderful to see the shift in how women and also how anyone coming from an underrepresented background is better supported in astronomy. The president of the American Astronomical Society right now is a woman. My department chair is a woman. The current president of the University of Washington is a woman. So seeing women in the field has become positively ordinary for me and for my students. And that's wonderful because that's not what it was like a generation ago. An interesting thing is that you look back and yes, the list of famous astronomy names are very male if you go far enough back in time. What I actually found really fascinating, and I learned it partly researching my book, was there were women doing astronomy the whole time. Some of the most incredible observations in astronomy in, the first half of the 20th century, where all the names you see listed are men, were taken by women. So women have always loved astronomy and wanted to do astronomy, and we just had a lot more barriers put in our way for a long time. There's stories in the book about women not being allowed to stay in the dormitories at Mount Wilson and at Palomar. The dormitory was nicknamed the monastery because it was only for men to stay in, and women still observed there. They just stayed in unheated cabins on the other side of the mountain, or their husbands would apply for telescope time and then they would go actually do the observing. And it's been really nice to see those barriers taken down because it was just putting hurdles in front of excellent scientists that were, spending time dealing with this when they could have just gone on and made the discoveries that they made anyway. So seeing that shape of the field change has been really great. It is not perfect yet. I have plenty of colleagues that would tell you there's still a ways to go and that there are still barriers to entry in the field, period. But it's definitely been great to see this shift in anybody who wants to do astronomy and who has the talent for it, getting more support and having fewer barriers in the way to do it.
Yep. Well, listen, it's been so great having you as a guest. And, you know, the next time anybody picks up a astrophysical journal or something and reads a dry account of a research project, they'll know that there's a lot more stories behind that research than is contained in that paper. As a token of our appreciation, we will be sending you a speaker's mug with our logo on it and all. But we really want to thank you, Emily, for coming on our show, and it's been very entertaining. And I don't know if anybody has any last questions, but otherwise, I think it's actually top of the hour. It looks like we timed it pretty good. So thank you again for being here. We loved having you.
Thank you so much.
Okay.